What's going on, everyone? Welcome back to Axiom. In today's video, we are tackling Bellman-Ford algorithm, and honestly, this is a game changer for your design and analysis of algorithms preparation. Pay close attention because this will definitely come up in your exams. Here we go. In graph theory, the single source shortest path problem asks a specific question. Given a starting vertex in a directed weighted graph, what is the minimum cost route to every other vertex in that network? The industry standard for solving this is Dijkstra's algorithm. It is highly efficient, operating an O of V plus E log V time, provided that all edge weights in the network are zero or positive. This diagram shows exactly why Dijkstra's algorithm breaks down if we introduce negative numbers. Dijkstra operates on a greedy principle. As its wavefront expands, it finds the shortest immediate path to a node and permanently locks that value in. If a cheaper path to that same node appears later by traveling through a negative weight edge, the algorithm cannot self correct. It simply ignores the better route, resulting in a suboptimal total. Advanced systems require negative edge weights to function accurately. It can represent energy recovery, cash back in routing, or logistical cost reductions. Because greedy traversal cannot backtrack to account for these negative variables, it is structurally insufficient. Processing these networks requires a comprehensive dynamic programming approach. That approach was pioneered by Richard Bellman, the mathematician who developed dynamic programming, a paradigm built to solve complex problems by breaking them down into smaller overlapping subproblems. Working at the Rand Corporation in the 1950s, Bellman coined the term to describe multi-stage decision processes where conditions vary over time. Concurrently, mathematician Lester Ford Jr. developed a similar method for finding shortest paths in networks. Together, their work forms the Bellman-Ford algorithm. Instead of a greedy node-by-node lockdown, Bellman-Ford uses a global iterative methodology. It evaluates the entire graph multiple times, refining path estimates with every pass. The algorithm intentionally trades time efficiency, running at a slower O of V times E for mathematical accuracy. It processes negative edges seamlessly and can definitively detect system breaking cycles that greedy algorithms miss. The mechanical core of the Bellman-Ford algorithm is a process called edge relaxation. This is the act of checking if the current known distance to a vertex can be lowered by traveling through a neighboring vertex. We initialize the graph, setting the source node to 0 and all other nodes to infinity. For an edge connecting node U to V, if use distance plus the edge weight is less than V's recorded distance, we update V to the lower value. Rather than looking at one localized path, Bellman-Ford performs a global sweep in a single pass. It checks every edge in the entire graph for these relaxation opportunities. This makes relaxation entirely self-correcting. If a new cheaper path is discovered through a negative weight edge, the algorithm will automatically re-evaluate and lower the node's distance on the next sweep. This raises a question of algorithmic convergence. How many global sweeps are necessary to mathematically guarantee that every shortest path has been found? This diagram shows a linear graph with 5 vertices to travel from the first node to the last as a simple path, meaning a path that never revisits the same node twice. You can traverse a maximum of 4 edges. In any graph with v vertices, the longest possible simple path contains exactly v minus 1 edges. Each global sweep of the Bellman-Ford algorithm guarantees that accurate shortest path information propagates at least one edge further from the source. This table tracks a dynamic programming process. With each iteration, the algorithm fills in shortest paths for nodes reachable within that specific number of edges. By reusing previously calculated paths, the graph resolves edge by edge, locking in the closest node's true values first. After exactly v minus 1 iterations, the algorithm has evaluated every possible simple path. The graph is forced into its mathematically optimal state. But what if a path isn't simple? A negative weight cycle is a loop in a graph where the sum of the edge weights is less than 0. If you travel this loop, your total cost decreases infinitely. In this scenario, a shortest path cannot exist because the true distance approaches negative infinity. Bellman-Ford handles this through its final step. It performs one additional relaxation sweep, the VT iteration. This diagram shows a negative weight cycle during that final sweep. The rule is absolute. If any distance is updated on the VT iteration, a negative weight cycle exists somewhere in the network. The math proves this. The longest simple path has v minus 1 edges. If a reduction occurs on iteration v, the path has v edges, meaning it visited a vertex twice. Because distance decreased, that loop has a negative net weight. The negative cycle acts as an infinite feedback loop within the system, continually driving the total path cost down toward negative infinity with every pass. By executing this VTH iteration, Bellman-Ford transforms from a path mining algorithm into a diagnostic tool capable of identifying infinite loops before they crash a system. We can apply this diagnostic capability to financial markets, specifically to identify arbitrage. Arbitrage is the exploitation of price differences across multiple currencies to generate a risk free profit. This graph models the currency market. The vertices represent individual currencies, and the directed edges are the exchange rates between them. An arbitrage opportunity exists if a trader can execute a sequence of currency exchanges where the final product of those rates is strictly greater than 1. This presents a computational hurdle. Bellman-Ford works by summing edge weights together, but tracking a sequence of currency exchanges requires multiplying those rates to find arbitrage opportunities. Using this algorithm, we need a mathematical transformation that turns a multiplication problem into an addition problem. We achieve this using logarithms. A core property of logarithm states that the log of a product is equal to the sum of the logs. Ln of A times B equals ln of A plus ln of B. Look at the currency graph. Instead of using the raw exchange rate, we replace every edge weight with a negative logarithm of that rate. This creates mathematical equivalents. Searching for a trade sequence where the product of the rates is greater than 1 is now exactly the same as searching for a cycle where the sum of the negative logarithms is less than 0. Through this transformation, a profitable arbitrage loop is structurally identical to a negative weight cycle. By running the Bellman-Ford algorithm on this transformed graph, we audit the entire market. If the weed iteration detects a negative cycle, an arbitrage opportunity is mathematically proven. We accept the slower O of V times E runtime because it provides a rigorous global audit that a greedy algorithm simply cannot perform. This same logic extends to network infrastructure, securing routing protocols like RIPE by preventing data packets from getting caught in infinite loops. Whether parsing exchange rates or mapping physical logistics, systems that rely on negative variables require a method capable of viewing the entire structure at once. Bellman-Ford provides the rigorous dynamic programming foundation needed to parse those negative variables, calculate the true optimal path, and prevent catastrophic. And there you have it. Bellman-Ford algorithm simplified. Remember, understanding the basics is key to cracking exams. Hit like if this helped, subscribe to Axiom for daily lectures, and comment below with any doubts. I read every single comment. See you soon.